Bon, mesdames, messieurs, on va reprendre nos travaux.
Ladies and gentlemen, let's resume our session. I will give the floor now to Sylvain WASERMAN. Is it WASERMAN or WASERMAN? How do you pronounce it? The new president, new chairman of ADEME, the Energy Transition Agency. He's been serving in this position for the last 6 months, this wonderful institution, which allowed the development of PV energy, wind energy, and also energy management. You have the floor. Thank you, Chairman.
Merci beaucoup.
Thank you very much, Chairman, ladies and gentlemen. It is a great pleasure to be here at the Collège de France. I was here last month to talk about green finance. So I'm delighted to return, and in this room there are many people who launched this journey of solar energy in France. So we should remember that the present is the result of past actions which made this result possible. So these are my first words for all these people who are committed to this field, who are very much involved and who have contributed to developing solar energy to the level it is at today. So thank you for that. Thank you for your commitment. So everything has been said this morning about the history of solar energy, so I won't dwell on the matter and I will dive directly into the next topic. I would like to share with you some information on solar energy and to say how much it is very much related to many challenges and paradoxes that I would like to share with you. The world of ecological transition has changed. I'm very pleased to join ADEME at a moment when, for a little less than a year, we have a specific figure to reach by 2030, by 2050, 270 million tons. So we have 7 years to find 138 million tons. And this changes everything because now we have a goal, we have figures, goals to reach. We know how much we contribute to the general objective. So we have a specific approach something we like in the industry and elsewhere to measure our performance in reaching this goal. So it's a new era of ecological transition, which is geared to analysis and results, because today there is an emergency and we need results. Solar energy has its role to play in finding those 138 million tons, because biomass and photosynthesis are natural ways to sequestrate carbon, and they are free. So we should foster them, and that's thanks to the sunshine. It weighs 10 million tons out of this big figure. And also PV energy is growing strongly in terms of energy power generation, between 5 and 10, according to the speed to which it will be developed in the coming years, but also because thermal solar energy is growing very much to meet industrial demands. I was at the inauguration at Verdun of the largest thermal solar installation of France, the second in Europe in terms of size, and its goal is to help the industrial process of Lactalis to help it in reaching its decarbonization goals. So solar energy, whether it is electric or thermal, has a major role to play in finding those 138 million tons. And now our common goal is to take it as far as possible in reaching this objective. At the heart of this ecological transition, and at the heart of sovereignty issues, I would like to share with you a paradox I was thinking of when preparing this conference. Solar energy is perhaps the most, the furthest energy, 140,597,000 kilometers. But it is surprising to see that it is also the nearest energy. It is the most accessible to all. If we look at our means of consumption, it redistributes our energy models, consumption, short circuits. It is accessible to citizens, to groups of citizens. So it is the furthest away and the nearest energy. And this is an interesting paradox, even more so since last week I was meeting. Yes, I had a busy week last week. I met the stakeholders of shared energy, associations, non-profits who want to involve citizens in renewable projects. And obviously solar energy is the top energy in this field, the most accessible and the one that can generate the greatest momentum for these citizens, those communities. Also, it is an energy which is it is the oldest and the most modern energy. The oldest energy because it's 4.5 billion years, solar energy, but also the most modern energy. And I've been discovering this since I've joined ADEME, because there are so many innovations in terms of solar energy, whether it is electric, solar, or thermal solar energy. And today we have 150 researchers based in ADEME. They are very much invested in state-of-the-art technologies, and we hope they will help us in reaching this energy transition. But when you look at, I was very much surprised when there was Solar Impulse, and Bertrand Piccard was showing us the extraordinary world tour he did in a solar plane. It was really amazing, and listening to him was very much inspiring. But also, we're talking about quantum computers, photons, technologies around photons. So science is very much developed on solar energy and associated domains. Also, solar energy is at the very heart of geopolitical challenges worldwide. We're talking about the Conference of Parties 28. Will it reach an agreement or not to phase out fossil fuels? Among the countries which have the most sunshine, like Saudi Arabia, they obviously have a windfall with oil, the presence of oil on their land, but they also have renewables that are being developed. But also geopolitical challenges with China. They're the greatest polluter in the planet, but they also have the most solar panels installed in the world. And so they pollute a lot, but they go very fast in developing new technologies, and they weigh as much as the rest of the world in terms of PV energy capacities. And if we look at our capacity to raise up to those challenges in terms of solar energy, and if we look at the entire value chain, I was talking to Mr. WASERMAN earlier, and France is the next exporter of thermal solar arrays, especially in coming from the east of France, and I didn't know that. But looking at these geopolitical challenges, it illustrates the complexity of the world. I was in Toulouse when our president was introducing the French program for 2050. And solar energy came through sovereignty and minerals and rare minerals or rare earths. And France is launching into a mapping of its territories to seize the opportunities, because solar energy shows our dependency for the production of panels and arrays, the use of these minerals. So these are some of the challenges we are facing. So I don't know if I can put a spotlight on your works. There are many experts who have worked within ADEME or who are still working at ADEME who are going to speak out today. But I have to say that to prepare this conference, I used ChatGPT, so I typed Collège de France, and I put the sun at the service of mankind. And the sentence that was the most pleasant was that the sun lights up our days. And I seized that opportunity to wish you a very successful conference, and thank you for your contribution, and thank you to all of those who contributed to making solar energy what it is today. Thank you.
Bon, sans attendre, nous allons...
So without further ado, let's move on to our second panel on scientific research. This will be moderated by Mohamed Amara from the CNRS. And again, I'm a timekeeper, and we are lagging behind schedule. We're behind our schedule. I don't want you to miss your lunch, so let's be mindful of the time, please. And if our speakers can join the stage, please.
Oh, je vais commencer. Hein. Bonjour tout le monde. Sinon, je vais là-bas. Donc, bonjour tout le monde. Enfin, j'ai vraiment le plaisir et même...
Good morning. I'm delighted to introduce this panel, this horizontal table and not round table. And it was mentioned by Denis Gottlieben earlier that after World War II, we had the first team from a structural point of view, the first team around thermal energy. They conducted their research, and 70 years later, when you look at this table, we have almost all the disciplines around solar energy, directly or indirectly. It has been said. We had thermal solar, PV, biomass, and so on. So this panel is very interesting to me. So first of all, let me introduce Stéphane Collin, a research director at the CNRS. Stéphane works on solar glass and cells which go above the Shockley limit. He will not talk about this this morning, unfortunately. He was the initiated with Jean-François Guimol of the PV Guide, which is a very good initiative to pass on the knowledge, this knowledge to the public, the general public. We also have Emmanuelle Delaporte, professor at the ENS of Cachan, the director, research director at GDR around the perovskites. We also have Valérie Keller, also research director, who will talk about solar fuels, something that is missing, that has been missing in the debate. She will explain that to us. We have Jean-Paul Cléder, research director at CNRS also, but also the chairman of the Photovoltaic Federation. And we have two more people. We have Delfina Munoz, coming from INES, and Cyril Kallio, who is representing the Federation of Solar Energy, FEDESOL. So Stéphane, first of all, and then there will be a Q&A session at the end.
Merci, Mohamed.
Thank you, Mohamed. So, indeed, I will not talk about my research, but rather I will talk about this guide, its infancy and why we created it, and just in a few minutes. It has been said at length this morning, photovoltaic solar energy has developed very rapidly, and it was quite unexpected. And what is the role it can play in energy transition? So at the genesis of this guide, we saw that these recent and very rapid developments are not factored in properly in debates. Sometimes there are mistakes or misconceptions because the discussions are based on data that is not up to date. So there are legitimate questions on PV solar energy. What is the cost of PV energy? Where are those arrays made? Is it polluting energy? Do you need a lot of energy to produce arrays? Do you recover this energy? I will not answer all of the questions, obviously. I'm just raising them. There's an issue around the dependency of the manufacturing of these arrays and the dependency on rare metals. So you have questions on installations today, societal issues, and the role of solar energy, PV solar energy, in the French energy mix. So we created a collective of researchers from the CNRS, and we created a workshop to meet those, to answer those questions and to create this guide, which answers all of these questions. This document, we wanted it to be freely accessible. So we published the first version in March 2022. We had very good feedback on this guide, so we continued improving it, and we published the second version with an additional 50% of content. And I will show you briefly what it looks like. Inside of this guide, you see some of these pages, what it looks like, the look and feel of the guide. We have some illustrations to explain what is a solar panel, how it can be used here. It is the manufacturing of a PV module, and each fact sheet is a question with an answer, very simple. An answer which deep dives into the topic for those who want that level of precision. And we wanted to work on the bibliography articles that were available, looking at recent research to answer those questions. So here you can see some examples, some answers that were provided. In this new edition, you have new topics that are addressed, topics that come from the feedback we had on the industry, the PV industry, the issue of rare or critical materials, the new ways of installating solar energy, floating PV, PV energy. So these are some of the questions that are addressed in this guide. So it is free of charge. You can download it with this QR code on this website. A few words on how we proceeded to create this guide. So we had a new way of working with a research collective. A collective made of researchers, and some researchers contributed largely to the second edition, for instance, Lamoureux de la Mare, and all the names you can see here. And sometimes some people contributed in an ad hoc, on an ad hoc basis, but this led to the creation of this very exhaustive guide. And I hope it will help the debate on the role of photovoltaic energy. And obviously, this is a two-way conversation. Our work is improved through the questions coming from civil society, questions on recycling and supply, the supply of critical materials and critical data also. So it's a two-way process.
C'est bon, je continue. Très bien, bonjour.
Good morning.
Voilà, donc moi je vais vous parler
I'm going to talk about a
groupement de recherche
research grouping within CNRS, supported by CNRS. It's a task force that was set up in 2017, and we are working on halide perovskites. And I'm going to tell you about this work in CNRS. You see that we have researchers coming from several institutes from CNRS. INP, so that's for physics, INC for chemicals, and IS, that's engineering and systems. So you can see the multidisciplinarity here. And, you know, it's good to have several disciplines working together, but we need to make sure that they can talk to one another. And so that's what we're doing. This task force is scattered throughout the country. You see that we have 175 French researchers, or French and foreign researchers, but anyway, they are located in 42 French labs. And we also have partners abroad in neighboring countries. You see the geographical distribution here. They cover the whole of France. Now, this new halide perovskite, this is the perovskite that actually started the work on this class of materials. You see, it's a hybrid type of thing, because you've got an organic part that is here, and you have the octahedrons here, which you can identify here. And these octahedrons are based on inorganic atoms. It's lead and iodine, and you have this little molecule here in between the octahedrons that makes the periodic arrangement. So halide perovskite is actually a crystal, and you can see here a picture of the crystal in question. It's black, just like silicon, and it has a certain potential to absorb the visible rays on the solar spectrum. So this crystal was discovered back in the 19th century. The structure of it was discovered by a mineralogist called Perovsky. That's why it's called perovskite. And then there were background studies, you know, mostly during the 50s and 60s, physical studies then in the 80s and 90s, but this was really in the background. And then around 2012 and 13, it started to be introduced in existing solar cells, and then it actually took the scientific community by storm, because we realized that it gave a good yield. Well, of course, at the beginning it was not very high, but it's a type of yield which very rapidly grew, actually, because the scientific community actually braced the optimization of the materials quality, the optimization of cells, research on physical and chemical properties of this crystal. And now the single junction cells have a yield which is very similar to those based on silicon. And we can also manufacture multi-junction cells that bring together a perovskite cell and a silicon cell. And today the yield is 33.9% and counting. So maybe in the future there will be a new record. A research group brings together a community. So this is what we've done here. I told you that there was an organic part and a hybrid part. So here it means that we need to combine the knowledge of different communities that didn't used to work together. You know, you used to have people working on models for organic semiconductors, people working on models for inorganic semiconductors, and here you really have to bring them together in order to combine the data, because we need new models. We need complementary skills. This is why we have a multidisciplinary team, and we also need to combine all those skills together. So we worked on several scientific avenues, of course, everything that has to do with photovoltaics. When discovering the physical and chemical properties of this new crystal, we are going to look at emerging developments like photocatalysis, for example. And you have a lot of challenges also to face with this kind of material, because it's a very, very complex type of material in its chemical configuration, because, of course, as you see, it's a crystal which includes several atoms. And the molecule that I showed you, you can play around with all its components. So you almost have all of Mendeleev's table there available that you can work on with this molecule. Then you have structural studies and defect studies also. This is really something that's crucial for the components, and we don't know much about those. You have physical properties, which once again are very complex because it's electronic, ionic conductor. You've got interactions between the bearers and the grid vibration. Everything has to be looked at. And of course, in a component, you have other layers around the material. So what happens at the interfaces? And of course, these are so many questions that we have to answer, because it's, of course, very spectacular. It's a very spectacular material, but there are a certain number of challenges. You know, I mentioned lead, so we have to address this issue. We still have also a stability issue that, of course, we're still working on. So this research grouping is going to give us tools to work together, to exchange knowledge and know-how, and to have a pretty well-structured scientific community. So we have our study days every year where we discuss the material, where we work on new projects, of course, because we want to try to attract funding. We have theme-based training sessions. We have workshops. We have also increased mobility, like researchers can go and visit another lab, and we also do scientific dissemination. We want to make this known to the general public, and these are all the projects that we are going to implement very soon. And thank you for your attention.
Bonjour à tous.
Good morning. I'm Valérie Keller. I'm a researcher at CNRS in Strasbourg. My institute is called the Chemistry and Process Institute for the Environment and Health. And I'm also the director of the Solar Fuels Research Grouping. And this is why I'm here today, to celebrate this anniversary with you in this very beautiful place. I'll try to summarize the work of this solar fuels research groupings.
Et donc le terme, la
And
carburant solaire,
when you
est
say
souvent
solar
associé à la
fuels,
notion de photosynthèse
very often people
artificielle.
think artificial photosynthesis.
Et le
I'll tell you
concept, en
why.
fait, de la photosynthèse
And actually, the concept of artificial photosynthesis or solar fuels is to try to store solar energy in chemical bindings in order to chemical bonds so that it can be used on demand.
on vient de voir
You know, more specifically, since this morning we've seen that solar energy is the renewable energy source, which is probably the most abundant and most accessible on the Earth's surface. But of course, we also hear that there are limitations to the use of this energy. And one of the main problems is that it's an intermittent energy source, and also it's not distributed consistently throughout the Earth's surface. And then there are other things that we need to work on. For example, how can we capture the photons at best in the most efficient possible way? How can we store this energy in order to be able to use it on demand? That is exactly at the time and place that we need it the most. So, you know that solar energy theoretically could meet the global energy needs of the Earth population, but of course there are a certain number of limitations. And we know that nature can overcome these limitations. But of course it's true that the time scale is very specific. So it's natural photosynthesis that is at play here. As you know, it converts small molecules, which we find in abundance in atmosphere, and into molecules which are of interest for life by using solar energy, sugar, carbohydrates, and this happens in the green part of the plant. And it's a process that happens with a moderate yield and with its own time scale, which is very specific. Now, what we have very humbly tried to do is to take our inspiration from this natural photosynthesis. It's called artificial photosynthesis. We try to do the same, to convert those small, abundant molecules with the use of solar energy into hydrocarbons that will be relevant for life, or into platform molecules that will be used or that will serve as energy vectors. So these are topics on which we try to work in our solar fuels research grouping. This is a summary of the scope of our work. Of course, the objective is to turn some of these small abundant molecules here into molecules which are relevant, as I said, by using, of course, solar energy. And in order to do this, we have to design molecules or materials to help us convert those molecules at best with the use of solar energy. For example, we are going to design light absorbers in the form of molecules or semiconductors. We are going to use catalysts or co-catalysts that will be molecules, materials, or enzymes, and we will also optimize photoelectrocatalytic processes. So, of course, for the moment, we're still in the embryonic phase here. We try to optimize these materials. We try to have a better understanding of the processes at work here. We, of course, are very reliant on advanced in situ methods And also, we resort to simulation and modeling tools. And the objective at the end of the process is to be able to design prototypes or photoreactors or photobioreactors even. Now, this is the second term of office of this research grouping. It started in 2016. It was a bit of a coincidence, actually, because we traveled and we met colleagues at other congresses and conferences, and at some point we found that there was a critical mass, a massive number of academics, researchers in France who were working on these issues, but of course each from their own angle, which were all complementary, because these were researchers coming from different communities which are all complementary to one another. And so the idea was really to use this complementarity and to foster this complementarity and to give more visibility to this network of researchers, very similar to what is done in other European countries, where you have networks of researchers who are pretty active on the topic of solar fuels. So we tried to give some structure to our network. You know, we have facilitators for each part of the project. The core of this, of course, is based on the elaboration of photoactive materials. And we are supported by theoretical approach, by calculation and modeling approaches, by advanced characterization processes, and we also try to work with chemical engineering experts in order to integrate or couple together these processes. And I only want to thank you now to finish. And like the previous speaker, I wanted to show you where we are all located on a map. There are 55 academic teams in France, and that's about 150 PIs. But of course, I wasn't so good at drawing maps, and so I could not draw the map to show you the distribution, to show you where we are. So you'll have to take my word for it. All those teams are evenly distributed throughout the French territory. So thank you for your attention.
Bonjour à toutes.
Good morning. I'm Jean-Paul Kleider. I'm a researcher at CNRS, and I'm not going to tell you about the outcome of my research, but I want to tell you about FED-PV. What is FED-PV? It's the Photovoltaic Research Federation of the CNRS. It's a unit that was created back in 2010 by 5 laboratories located in and around Paris, and now in 2023 we have 18 labs distributed throughout the country, as you can see on this map. Most of these units have a lot of researchers working on photovoltaics. We have about 200 and 220 people actually working in FED-PV and who belong to all the labs which are mentioned here on the map. Now, what is it? And what is it for? Well, it's a federation, meaning that the objective is to bring together the French academic forces and to bring together the academic community working on photovoltaic solar power. This morning we heard a lot of presentations which show that there is a history related to photovoltaics that goes back a long time. But what we found 20 years ago is that all the labs working on PV tend to work on their own independently, and the purpose of this federation is to bring them together. So we decided to not give you too many figures, but rather to show you the topics on which we are researching right now. This here is a summary of what FED PV labs are working on. You have 4 axes here, 4 yellow arrows, which are actually based on the materials that we're looking at. So you've got silicon, massive silicon, or thin layer silicon. You have thin layers of other types of materials, 3, 5 semiconductors or chalcogeners. Then you have the organic thin layers and perovskites that Emmanuel has told you everything about a few minutes ago. And then you have activities which are located at a very early stage of the process with emerging materials or new concepts. And then, if you look at the 3 cross-cutting arrows in green here, you see how all this work is supported. It's supported by theory and modeling. It's supported by multi-scale characterization. This has been mentioned by my colleagues also. We need to characterize the products at several levels. We need to have diagnosis tools which are accurate and reliable. And then there is another avenue which has to do with photonics and nanostructures. And this is what Stéphane Collin is researching, actually. And it's also cross-cutting, because the idea is to better absorb the sun's photons and to make all the materials thinner. And you see that all the yellow arrows point at something which is called the tandem cells. This is really a subject of research in France and everywhere else in the world. The idea is to combine the different areas of research in order to have materials which will have a yield that will be superior to what you might have if you're using only one single material like silicon, for example. And then, once you've got those cells, you need the modules, and you need to operate them. So you have a lot of research also on the modules and systems. Somebody this morning was talking about power electronics. Well, this is exactly what we're talking about here. It's a key element for the actual implementation of photovoltaics. And then all of this, of course, aims at having more efficient and less costly systems. Now, I wanted to show you some examples of the actions carried out by the Federation, which have been leading since 2020. We have decided to organize scientific days in the French regions, in the provinces. We had 2 in Lyon, for example, this year. The idea is to go outside of Paris and to see what activities are being carried out in the area of PV. We also provide support to open science. This is really important for us researchers and for the CNRS at large. And the researchers of ADEME contribute to the European Physical Journal, Photovoltaics, and we also contribute to support some scientific events. Like you have here a picture of Becquerel, because it was the 100th anniversary of his birth recently that we celebrated. And we also provide support to a certain number of scientific organizations. And Now, to finish, FED PV created the Journée nationale du photovoltaïque, so national photovoltaics days. Actually, it's a type of event in which we really want to bring together the national community. It's usually a 4-day working session, usually in December. We actually had the last edition last week. It's a residential type of thing. We stay in the same place for 4 days because this develops the links between researchers, and we have training sessions. This is really important because we have to train young people. We have scientific sessions, of course. We have poster sessions, and also what we want to do is to open up to civil society. This is why we have debates and conferences which are actually opening up to the industrial world and to civil society at large. And those seminars are very popular. We have about 120 people attending every year with a high proportion of PhD students and post-PhD students, because that's what we want to do. We want to pass on the torch of photovoltaics to younger generations.
Good morning.
I'm Cyril Caillot, representing FEDESOL, which is the CNRS entity led by Cyril, which was created in 2011. There are a certain number of people who participated to the creation who are in this room. It was supported by the Derby competitiveness cluster represented here by Mr. Joffre. So this Research Federation on Solar Energy aims at bringing together a certain number of skills and knowledge and to coordinate multidisciplinary research. It's a forum for discussion made up of researchers and PhD students, postdoc students, coming from 33 labs and sharing their knowledge. They also have test procedures, and they work on a certain number of prototypes in their labs. It's a multidisciplinary federation that has connection with national and international research networks. Every year, we organize the JNES, the National Days for Solar Energy, bringing together about 100 participants. And we also have theme days in DAX. And we have a lot of webinars. And it's a research federation that works on 4 main directions. That is buildings and solar cities, the first one. The aim is to foster access to resources by using urban spaces for the production of heat and power. We work on how to integrate solar components on buildings and how to deploy this at the scale of the country. Then we have concentration solar power projects in which we try to reduce the cost of these solar power plants, which produce heat for the industry and power and fuels, and they work on gasification, for example. One of the key platforms here is the PROMES laboratory, led by François Robillot. They have a lot of power balls, including the 1 megawatt solar furnace. In that area, they look on materials property, the coupled transfers of heat and materials, and the control and monitoring of the plants. Photo processes, that's the third area of projects. The idea is to control solar photoreactive processes for the production of bioorganic molecules, biogases, biofuels, and to depollute water and effluents. We have a very multidisciplinary community working on multi-scale programs, and it also brings together 3 experimental platforms, one in the west of France, one in the center of France, and one in the south. For storage, we have research on the variability of solar resource, on how to balance the supply of energy based on demand. And the storage, of course, has to be taken into account right from the design phase. It's storage by absorption or adsorption. There are 3 challenges here: the energy side, then there is the financial side, of course, and then there is the environmental impact of the storage facilities in order to secure production, to ensure availability and recyclability of the materials, and to make sure that the carbon footprint is under control. And there is also another transverse avenue which brings together skills and knowledge on many topics, mostly working on modeling and the use and reuse of resource based on the integration of several processes. We resort to artificial intelligence, and then we have a life cycle analysis, of course, which cover all the project areas. And I would just like to tell you about something new that researchers are working on. They're working on low-techs. Because of the life cycle analysis, we have started to research into that area, and this is what's new in our research group. Thank you for your attention.
Bonjour à tous.
Good morning. I just wanted to thank Mohamed, Daniel, and the entire team for having invited me. It's always a great pleasure for me to come to Paris from time to time. That's where I started my career in the photovoltaic after Spain. Now I'm at INES at the CEA. And INES is a research institute in Chambéry. It belongs to the Grenoble CEA and to the LITEN through the Department of Solar Technologies. So INES, there are some 500 people working there with research teams working on the entire value chain of the photovoltaic. And they're working on the technological development, that is the technological transfer. And we are going to work with all the teams of the CNRS in fundamental research to try to transfer it to the industry and find technological solutions close to the market. So that's the positioning of the INES. We're going to cover the entire value chain. I really liked the presentation from Jean-Paul with lines. We're going to talk in circles because that is the objective of the photovoltaic. That is to have a circular economy. And therefore, we are going to develop material physics, silicon, and new material that was presented like perovskites. We're going to integrate that in the cells, so the manufacturing of the cells close to the industrial scale with equipment that are compatible with the industrial processes, and we'll be able to manufacture the modules, either standard modules or modules adapted to specific applications. For example, modules adapted to the spatial area, floating PVs, and objects according to the flexibility, the weight, etc. We're also going to work on the architectonic adaptation, the scale. We're going to integrate them, test them, And after the results of the tests at Lindon in the laboratory and in real conditions, we will work on the material, on the physics of the system to improve the initial material. So this is the eco-design approach, to use less material, to make them easy to recycle, and so that the value chain might not impact the natural resources, and so that it might be better accepted by society. As mentioned earlier on, we also have an important societal work to carry out. And we have a whole channel working on the systems, network integration, on the storage, the use of this energy for transportation, mobility, and all this in this site of Ines with different teams, with different specialties. Now, to give you an example, this is a picture of our pilot line for the manufacturing of cells. So we work on real cells at the industrial level. We have efficiencies of 25% with less use of material. We're going to try to find the limitations of silicon so as to accompany technological transfer towards industries in Europe, in France. Those who are interested in the manufacturing of cells and photovoltaic modules in Europe will also be developing, and we do it a lot with the CNRS labs, the ones I knew of in the past and the ones that I'm discovering today, for the tandem perovskite silicon tandem, to assess this technology, to see whether we can use it over a larger industrial scale, to see if there is any meaning to have an industrial process, to see how much time it will take to get this done. And we're going to increase the technological maturity of each technology for all the aspects regarding modules and integration. So we do this, and we're working on other topics also related to the value chain of the photovoltaic. Thank you for your attention. I was quick, but I'm at your disposal if you have any questions. Good morning. I will try to tell you about the marine aspect. Gregory Pinon, I'm professor at the University of Le Havre, Normandy, director of the GDR CNRS EOL EMR on marine current power. So the GDR EOL EMER is GDR on all the marine renewable powers, the marine turbines, SWOC, seawater air conditioning, etc. Today I realized that I've forgotten the floating solar. Sorry about that. I'd like to apologize. But also the terrestrial land wind farms and offshore wind farms. I like to focus on offshore wind farms because I wanted to convey a message. I hope it will be interesting for you. And the link with my invitation here today, apart from the marine turbines, from lunar attraction, all these energies come from solar radiation through a succession of thermodynamic transformations. Of course, I'm not going to make a presentation just as all my other colleagues. We have an internet site with all our researchers. We have 200 researchers in the whole of France and some 40 labs. Now, in terms of our positioning, why did I want to focus on offshore wind farms? Well, there's a lot of transformation at GDR and in all the French labs. So therefore, So the offshore wind farms, I took the information from the data lab, and from 2019 to 2021, we see that the offshore wind farms are at zero, and that's really unfortunate. And even if we round it off, it isn't wrong. So the objective for 2023 is 2.4 gigawatts, and over the longer term, 5 to 6 gigawatts. I'll try to go a little further. If we look at ADEME scenario, I wanted to present the two ADEME scenarios. So the PV times 11, and when this is 45 gigawatts installed, it's times 11, and I've put times infinite because if we start from 0, 2021, it is times infinite. I have a small weakness for the M0. PV would go to 208 gigawatts times 21, and for us it would be 62 gigawatts of offshore wind farms. And actually, there's a lot happening. You probably have already seen this slide that is from the 1980s. The turbines were very small with very low powers. I think it was 0.5 megs, a few kilos. You see the growth? Now we have larger turbines. At the time, it was 8 to 10 gigawatts with a question mark. And that's what I want to talk about. Currently, the turbines are roughly at 12 megawatts. So this tells you the power, but if we talk in terms of power, it is always a little complex. And this was mentioned earlier on. As for what is manufactured in France, this turbine, the Haliade X 12 megawatts, it's manufactured by GE in the Pays de la Loire, and the blades are manufactured in Cherbourg. There is the equivalent of Siemens Gamesa. They have plants in Le Havre, and they manufacture turbines and nacelles, and they have 3 plants, 2 major ones. And what is interesting is that this is mentioned here, but we often talk about power, 12 megawatt, but what is important is the load factor. And for these turbines, multi-megawatt, large power, we have a load factor of 300%. And what is interesting here is to compare the production of an offshore wind farm, the one we're discussing about. You know that there's a debate currently on the sea for the future wind farms. And I tried to compare very quickly the electricity, the energy produced with a nuclear reactor, an EPR type of 1.6 gigawatt. So the load factor, I've taken the calculation, the average in the past few years, 75%. Maybe I'm a bit optimistic, I agree. And actually 1.6 gigawatt times, that's 8,760 hours. That's the number of hours per year, times 75%. So if we round off, it is 10 terawatt hour. So the farms that are being debated, it's roughly 1 to 1.5 gigawatt. But to make a good comparison, so it might be a good representation, I took a farm of 1.6 gigawatt. The load factor, 63%. Well, honestly, we've studied them, and the return we have in Europe is roughly this amount. It can be easily explained. It's 63%. So we have some 9 terawatt hour. So when I was a little child, this turbine that we were shown when we were on the beach, well, this is comparable to the production of a French nuclear reactor. Today, the test machines are roughly 15 megawatt, and we are developing turbines of 20 megawatts in our labs. So if we divide the 1.5 gigawatt, that is 100 turbines of 15 mega, or 75 turbines of 20 mega. So in terms of space, it isn't very invasive. So I wanted to be brief, and I'll keep my promise. As for the GDR, EOL, EMR, I couldn't show you all the technologies, but this is the message I wanted to convey. From the industrial point of view, there has been a huge growth, a huge industrial development, and in our research activity, it's the same thing. I've put a hyperactivity which is extremely sustained in a lot of European countries. Today, in France, we're doing the same. These are our themes: the reliability of the machines, mechanical, electrotechnical, converters, the fluctuating loads because of the wind, turbulence, the cyclic load, the waves, the extreme load in case of storm, the impacts of the waves, the manufacturing of the blades. I went and visited the Siemens Gamesa plant with the blades of 110 meters, new blades that can be recycled. They can be recycled. We have to use the right process. And the manufacturing processes, the new multi-megawatt generators, the different ways of using them. They just installed the floating metallic, concrete anchoring if necessary, the environmental impact, the human science and social effects, receptivity, socio-economic impacts, visual acoustic, environmental impact on the fish, fauna, flora, megafauna, the carbon footprint, the life cycle, the needed material, sustainability, etc. Thank you for your attention. I hope that I've brought you some sea freshness here.